Welcome back, class. Let's start the second session for the rigorous method. So before we go to the other example 4.5, let's recap uh, the gist of design spec function. Okay? So under regfrag, as you know, and as we practice in example 4.4, you can actually set the targeted purity of your product, and then you can use design spec function to identify the operating parameters for your distillation column. So design spec can be specified inside the regfrag block using the design spec and vary forms, as I informed you before. So this is a little bit different from the design spec function that we used before, which is under the flow sheeting function. Okay? So you can actually use both, but if you are having a decision process using regfrag as a simulation model, then I would encourage you to use the design spec function under the block uh, area. Okay, so one or more regfrag input can be manipulated to achieve specification on one or more regfrag performance parameters. So the number of specs in general should be equal to the number of varies. Okay, so bear this in mind, the number of specs that we include should be the same with the numbers of varies. It's just like in example 4.4, we have actually included two specs for the targeted purity of the product and two varies, okay, uh, which varying the parameters like reflux ratio and also the distillate to feed ratio. Okay. So the design spec function and also varies function in regfrag are actually solved using a middle loop approach. This is a mathematical approach to solve the equation, and if you get an error saying that the middle loop is having a problem, like it's not converging, then you have to check the design spec or varies that you have included, meaning that your target may not be logic, or the varies or the range of parameters that you have included is also actually illogic, right? So just check the design spec and also the varies value that you have included. So let's start example 4.5. Example 4.5 is the same case with example 4.2. We need to design a column to separate N-butane from cis-2 butene. Sorry, there's a typo error here. This should be butene, right? So the feed information is as follows. We have vapor fraction 0.5, the pressure is 1 bar, and the feed flow rate for N-butane and cis-2 butene is 50 kilomole per hour each. Okay, so you have to use Wing-Robinson as a property method and simulate the distillation process to determine the purity of N-butane in the distillate product in mole percent, and determine the column operating parameters to achieve the desired purity of N-butane of 99 mole percent in the distillate product, and estimate the diameter of column if sieve tray is used as the internal of the column, right? I think the first two questions are the same. With example 4.4, we have to use the same approach. On the new one would be C. Later on, I'm going to show you how to predict the diameter, the column diameter from regfrag model. Okay, now I will skip some of the steps because it's quite straightforward. Okay, the initial step is you can just use the approach as practiced in example 4.4. So of course, before you do the simulation, you know that you need the information like number of stages, reflux ratio, and also distillate to feed ratio from the simulation results of the STWU. So simple, because you have done the STWU simulation from example 4.2, So you just extract. So this is a simulation result from example 4.2. So remember, these results was generated with errors, but we can ignore the errors because the errors is actually about the reflux ratio that we guess is actually lower than the minimum reflux ratio. So uh, the software has actually taken the corrective action to calculate all these simulation results accordingly. So we can just take it as it is despite the error. So then you have to create the blank simulation, select the components, select property method, run to generate properties for all components. Then you shift to simulation tab, construct the flow sheet, include feed info, include block info, then run simulation. Okay. Now, so if you follow all the steps given in example 4.4 and run the simulation, you can actually generate the results without error. Okay, you have results available here, the status. Then you check the result stream in order to get the answer for question A. Okay, the purity of butane in the top product in the distillate, right? So go to stream results, and remember we have to get the mole percentage. So S2 is our distillate. So check the butane component. The composition is about 98.59 mole percent, right? So this is the answer for question A. So let's move. So in order to answer question B, as usual, we have to set up the design spec under the block T101, and you have to create the new design spec. Just click new, and then you have design spec 1. So this will turn up design spec 1. So this is a page for you to put in the design spec details. So remember, we have to target 99 mole percent of N-butane in the distillate. So you have to select under the spec, you select mole purity and put the mole percent in fraction basis 0.99. Then you proceed to component tab and feed or product streams to put in the details of your design spec. Then you run yet to run the simulation. Another things that you need to include is design spec and vary must come in pair, right? Okay, now vary you can either vary reflux ratio or distillate to feed ratio. I leave it to you, but here I have actually shown you how to vary the reflux ratio from 1 to 200. So just create a new vary 1, and then this is the input that you need to include. Okay. Now after you have included all this, then you just if you don't know where to go, then you click next, and you'll be guided to run the simulation. So once you have run the simulation, you can actually check the results under vary. Okay, under vary. So in order to achieve the 99 more percent of butane in distillate, the reflux ratio recommended is 33.125. Okay, so this is the operating parameters that you should set in order to get the targeted purity. So this is the answer for question B. Okay, let's move forward. Okay, now in order to answer question C, you have to set up the column internal under the block of T101. Okay, you have column internal here, so just add new, then you have int1 internal 1. Okay, internal 1, and then you have to include the column internal details under the section. So there's a tab, the section page. So this is a section page. Just click, okay, then you will be guided to a section page. So this is a section page. Very simple because we only use a the sieve tray as an internal column for the whole column. So we don't divide the column into a few sections. So meaning that from stage 2 to 82, it is actually with the sieve tray internal. Okay, stage 1 is condenser. Stage 83 is reboiler. So the number of stages that we have put in the configuration of column just now is 83. So therefore the column internal only applicable to stage 2 to 82. So you just choose is tray type. Yeah, this one, the mode, you just leave it as interactive sizing, no problem. This is the default setting. So the tray type is sieve, just choose, and then the rest I think you can just leave it. Okay, so once you have put in all this, the diameter will be predicted automatically, adopting the same approach that you learn in unit operation, meaning using the properties like viscosity, velocity, the Weber velocity in a column to calculate the diameter of the column. So you have here the diameter. So the diameter predicted is 3.454 meter, and this is the answer for question C, right? So not very difficult. With software, you can actually calculate the diameter, the column diameter easily. Okay? But of course, before you use the software, you have to learn the principle. Okay. Before we end the session, let's go through some problems that you may encounter when you simulate using RedFrag. So if a RedFrag column fails to converge, okay, that means you are getting a message saying that simulation results with error, and the message is because of the failure in the convergence. Then you can do the following. So first, check the physical properties issue. So you may have chosen a wrong property method. Okay, please check. You can check in any other references, reference book or journal papers, right? And second, ensure the column operating conditions are feasible. So make sure the operating condition of your column is logic. Okay. Of course, it is based on the chemical engineering principle. It must be logic, right? So the third, if the column error or tolerance is decreasing fairly consistently, so you have to increase the number of iteration on the RedFrag convergence basic sheet. So there is, if you check the block, under the block page, there is a sheet called convergence. Okay, so you can go there and check the error or tolerance. So typically, I think can't remember. I think maximum, the default one is maximum iteration is 30. You can increase up to maximum 200. Okay, if when you check your error or tolerance is actually decreasing with the number of iteration, then only this will work. You try to increase up to 200. Of course, time taken will be longer. It's just like the iteration you have done in the class. The more iteration you do, it will take longer time. Okay. Fourth, in order to overcome the problems occur, you can also provide some estimation, like temperature estimation for some stages in the column using RedFrag estimate temperature sheet. Okay. So this is particularly useful for absorbers, and you can also provide the estimate for some of the stages in column using RedFrag estimate liquid composition and vapor composition sheet. So this is especially useful for highly non-ideal system. If you have this information, if you don't have it, then yeah, please do not put. You may, if you put the wrong one, then yeah, you are actually farther from the answer, not closer to the answer, right? Okay. The last point is experiment with different convergence method on the RedFrag setup configuration sheet. So in the RedFrag setup configuration sheet, you can actually change the convergence method. So for example, if you are having a highly non-ideal system, then rather than using standard method, the default would be standard method, you can change it to highly non-ideal system. So this is, I think all this is actually useful for you when you have your plant design project later on, because you'll be given a totally different case, and this case may deal with a highly non-ideal system, right? Okay. Uh, for this particular part 2 for rigorous method simulation, we have actually prepared one exercise about methanol and water separation using a distillation column. So here, the information given here is actually quite comprehensive. So looking at this, I would say you don't even need to run the DSTWU before you do the regfrag. So you can just use regfrag straight away to answer question A and B given here. Okay, there are A and B question. So I have actually highlighted here, the STWU is not needed. If in the case of all this information is not given as example 4.4 and 4.5, then you have to first generate the simulation results using the STWU in order for you to proceed to regfrag. If not, you may have difficulty to put in the details of the regfrag configuration. So let's check the progress of your learning. As usual, you have to go through quiz 4 before 10th of June, 11:59 p.m. Okay? But before you try all this, make sure you have achieved the learning outcome for this particular topic, okay, which is the simulation of distillation process using regfrag. So first, make sure you know how to describe the rigorous distillation model. Okay. Second, you should be able to identify the minimum input required for the simulation of distillation process using regfrag. As I said, if you don't have enough input, you have to first run the simulation using the STWU before you proceed to regfrag. Okay. So we shift to the third point. Make sure you know how to determine the best operating parameter to achieve the desired product purity using the function of design spec under the block if possible. Okay. So the fourth one, the last one. So you should be able to know how to estimate the column height and also the diameter using regfrag. Okay. Diameter, no problem. I have actually shown you how to estimate the diameter. So if you know in terms of column height, it is also related to the number of stages. If you know the number of stages in the column and the spacing in between the stages, then you are able to predict the column height. Okay. Typically, the default setting, if you look at the place that we set column internal just now, the default setting for the space in between stages is about, I think 0.6 meter is about 2 feet. And you can check later on. And with that information, you are able to estimate the column height. So I think with this, I would like to end our session. So this is the last slide. And thank you very much. I hope you enjoy. So any question, we can discuss during the discussion forum later on. Thank you very much.